probably bigger than that. So that kind of
betul
force,
lah.
this particular area must be sufficient enough. Okay, must be
Kalau kita
sufficient
menang,
enough or must be strong enough.
oh,
So for
kita
it
dapat tu nak
to
buat
be able to hold the force that applied, when you pull the tendon. So if it's not being reinforced, when it's not being, reinforcement is not being provided sufficiently at that particular area, so there will be a possibility where, that particular area might break, might, degraded, might crack, might burst, and so on. So to avoid that from happening, so normally we're gonna design a certain length, and we're going to provide a sufficiently numbers of shear link at that particular area. So that's why the name of this structure element part, we call it as an en bloc design. Okay, all right. So what will be that's the overall view of today's topic that we're gonna cover. So what will be the learning outcome from this topic? We'll be able to calculate the transmission length of the pre-stressing wires. Second, able to calculate bone stresses developed between concrete and steel, because we have tendon and also the material of concrete. Able to determine the stress distribution, able to calculate the bursting tensile stresses in en bloc. So we need to calculate what will be when we pull the tendon, we can estimate how much the stresses that can cause the bursting that might happen, so that we can provide sufficiently how many numbers of reinforcement that we need to provide to avoid bursting from happening. Okay, all right. So en bloc. So as we mentioned earlier, so normally it will be when we say like post tension member, so the force is concentrated over a small area at the end faces of the member, and this leads to high tensile forces, okay, at the right angles to the direction of the contraction force. Okay, so this effect will extend from the end of the member, which we call as the transmission leg, until the compression has distributed itself across the full concrete cross-section. Because the most critical part will be, of course, near to the force, when you pull the tendon. But as the load or the stresses is being like gradually distributed, so it will be lower down. Okay, so this region is known as en bloc, as we mentioned, and must be heavily reinforced by steel to resist the bursting tension forces. Okay, so en bloc reinforcement will generally consist of closed link, okay, which surround the anchorage, and the quantities provided are usually obtained from empirical methods. So for this en bloc design, normally it's critical for post tension, not so much on pre tension, but it doesn't mean that we cannot design. Okay, but normally it's much more critical for post tension. Okay. All right, so we have the anchorage zone failure, right? Because for post tension, normally there will be assistance of anchorage, because post tension we have to provide ducting and we concrete first our pre-stress beam. Means that the concrete is already hardened before you apply your tendon. So it means that in the ducting itself, when you pull the tendon, so the force applied where lock it with the anchorage and all. So near to the part of the process whereby we have to design sufficiently reinforcement for our en bloc. Okay. So anchorage zone failure due to uncontrolled cracking or splitting of the concrete from insufficient transverse reinforcement. Okay, so bearing failures immediately behind the anchorage plate. Normally. So it could happen behind an anchorage plate are also common and may be caused by inadequate dimension, okay, of bearing plates or poor quality of concrete. So might be the reason why failure might happen, specifically at the end at the end part of our beam. Okay, so this picture is shown like I sketched here, right? So you can see it's located at the end of the member, and you can see that there is a how to say, bursting reinforcement shear is provided, is designed at that particular part, and this is where the tendon is fully anchored, anchorage. So this is a good example of showing how much is actually at the end block is being reinforced. So when we say this one is the wedge or the anchorage part of our tendon, and this is where wedges, so where we lock the position of your tendon, and stopping it from, return back to original length when you pull it with a certain force. Okay, and this is where we can see that inside here, all right, inside here is the ducting, right? So where we can slot in our tendon, and surrounding the ducting is where we're going to provide sufficiently reinforcement. So shearing, it doesn't mean that it's only like the square type. It could be a circular type. It really depends on the design and how much critical is the end block condition that we want to design. Okay, so all these things, all this behavior is happening due to the Hoyer effect. All right. So what we call as a Hoyer effect is whereby we have the applied force. Okay, so this is the applied force when you pull the tendon. So when you pull the tendon, technically what is happening inside here, where you have the radial pressure coming from the material, the concrete, and the friction when you are pulling your tendon. So this reaction between these two different stresses, okay, where we call it as a Hoyer effect. Right, so this is the Hoyer effect. All right, so then this will cause like what we call as a radial pressure inside your end block. Okay, so as what we mentioned before, when we want to provide our shearling, okay, towards the end of our end block, so we want to know how long we need to provide. So the length of it we call as a transmission length. So this is a transmission length. So transmission length can be calculated, okay, based on Eurocode, whereby we can take it as a LPT as the transmission length, and it will be alpha 1, alpha 2. So it really depends. Alpha 1 depends on the release of the tendon. So it could be gradually released or it could be sudden release. So both will have different value. One is 1 and one could be 1.25. So when we calculating our transmission line, so we also have to know what kind of method, in releasing the tendon that we're gonna apply or we're gonna use. Another parameter will be alpha 2. So alpha 2 will be really depending on the type of tendon. So we have so many types. Okay, so this type of tendon will give you the coefficient value, different coefficient value. For example, we have round wire, we can use 0.25. If we have 3 or 7 wire strength, at one, so we can use it 0.1. All right, and the phi is your nominal diameter, right, as we know, and then you have the stress, which is your P divided by area of your tendon, AP, and the bond stress. So the bond stress here, which is represented by FBPT, it can be calculated by taking the mu P1. Right, so mu P1 is really depending on the coefficient type of your tendon, which is if it's inducted wire, we can take as 2.7. So if it's just a strand, you can take it as 3.2. So it gives you two different values for your mu P1. And then we have another parameter, which is mu1. So mu1 is the bond condition. So this bond condition, you have to decide, is it your tendon is a good bond, or is what we call, or if say that you cannot consider it as a good bond. So then you can decide to use either you want it to be 1 ataupun 0.7. Okay, so means that 0.7 will have some kind of partial is some kind of factor or safety, to ensure the condition of bond is taken into consideration when you're calculating your transmission length. All right, so then you have your design tensile strength. okay, of concrete at the time of release. So at the time of release, whereby when you put tendon, you release the tendon. So this will really depend on this formulation, whereby SCTN is the tensile at the time of release. Okay, and you can take the coefficient of your gamma C concrete equivalent to 0.1. Okay. All right. So another this how to say, the transmission line should be taken as the less favorable of two values, which is we have two values. One is LPT1 and one will be LPT2. So both will be multiply your transmission line that you calculated before, multiply 0.8 for LPT1 and you multiply with 1.2 for LPT2. So these two values, you have to take the most minimum. So normally lower value is used for verification of local stresses at release and the higher value for ultimate limit state for shear and accuracy design. Okay. So when we are calculating LPT, it also can be, there are two ways. Like one, you can calculate it through the formulation, or else you can use the whatever given in the formulation, whereby it's taken as beta B multiplied with or say omega values or diameter. So we have the wire diameter, okay, and we have the beta B. So beta B is taken based on your concrete grade and also the type of your wires of your tendon. So then it will give you what will be the value of beta B. Then you can put it into the formulation for you to calculate your length, transmission length. Okay, all right. What else? So in terms of, if say that you have to design your M block for pretension, okay, means that normally you're going to provide those minimal reinforcement there for pretension, but still has can be provided or has to be provided. Okay, so transverse tensile level in the transfer due to concentration standard at the M block. So an acid of a horizontal cracking might occur. So therefore, when we want to provide our reinforcement, our shear reinforcement, our ASV, so we can take this formulation into consideration to calculate how much actually the area of reinforcement that we need to provide to tackle for en bloc condition. Okay, so you can take 2.5 multiply with moment divided by Fs strength of steel multiply with height of the beam. Okay, so that is for pretension. All right, for post-tension, as we mentioned earlier, en bloc design is very critical for post-tension. Okay, because of the pulling of the tendon is taken into consideration before concrete is concreting. Sorry, after concrete is concreting. Okay, so when we have a post-tension beam, so this is technically there are two different anchorage that you can use for pre-stress. One, we have what we call as the plate, flat plate. This is the flat plate, right? And one we call it as a conical anchorage, means that it's being penetrated into the beam. Okay, so if you look into the trajectory of the stress, the flow of the stress itself, so you can see the difference of it. The concentration is normally at near to the load applied, right? So this is where the critical part comes, whereby this is what we want to try to cater actually for the LPT. Okay, and for conical, this is conical. It mentioned conical because of the shape. It's like this. All right, but then the trajectory of the stresses is a bit different because you have it more curvy like this, rather than the conical, rather than the flat plate type. Okay. All right. Boleh, guys? Any questions so far? Soalan? Okay. Hopefully bila suruh diam tu maksudnya tak ada soalan lah ya. I'm not sure what you guys are doing. Hopefully at least you listen to it. Alright, so we have this is the another example of the path stress trajectory. Okay, happening in the pre-stress. So if it's a 1, so it's quite similar with what you have here. All right, but if you have 2 like this, so it's a bit different because you have 2 different parts. So it depends on the width for each Y. Okay, all right, don't want to go here. It's okay because Okay, so now when you want to design our en bloc, okay, so we need to check our bearing stress behind the anchorage plate, right? So this is what we want to do. So we need to check our bearing stress, okay, behind the anchorage plate due to the pre-stressing force, okay, which does not exceed the limit of FRDU. So maknanya we have to calculate the limit first. All right. So for pre-stressing for the limiting stress at FRDU, so we have formulation of 0.67 FCK, AC1 and AC0. So what is AC1, AC0? AC1 is where it's a maximum area having the same shape as AC0. Okay, sorry, AC1 and AC0, which can be inscribed in total area of AC. So means that AC0 can be taken as total area of AC. So AC0 is the loaded area of the anchorage plate. When you have your anchorage, there will be a certain area covered by the anchorage. So that particular area is called AC0. Okay. All right. So when if we say that you want so when you want to look into the how it is being considered, all right. So it's actually represented like this lah. All right. So you have AC0, okay, which is the, if you look into the definition, is the loaded area of the anchorage. So that is that particular plate. In this case, the how to say the anchorage is a circle lah, right? It's a plate, circle plate. So then you have AC0 as the anchorage plate and AC1 as the maximum area, right? If you can describe the total area of AC lah. AC. So means that this is the total area of AC. So this part is the total area of AC. Right? So it's the maximum area having the same shape as because when you have your anchorage is circle, so the whole area for you to estimate your AC1 also will be circle. All right. And what else? So you have, this is the strut where you take the resultant of the forces due to the forces applied by the tendon, which is horizontal. So it will spread into a triangle how to say calculation. Yeah, so you will get like 0.5 T, 0.33 T, and also 33.7 T. Okay, so that is the I would say the common parameter that we use here. And the lateral tensile bursting forces can be established by the use of scientifically determinate strut and time model, where it is assumed that the load is carried by a truss consisting of concrete struts and also link of reinforcement acting as steel ties partial to 1.2. Okay, so this will be all the values that you can calculate according to strength, reinforcement, design, and so on. Okay, so design consideration. What will be the design consideration? So a deviator shall satisfy the following requirements. So means that the withstand of both longitudinal and transverse that the tendon applies to it and transmit these forces to the structure. And second will be ensure that the radius of curvature of the pre-stressing tendon does not cause any of the stressing or damage to it. So you can see this is a very typical flow.
Yeah.
All right, typical flow of your stress trajectory or the stress path, from your flat plate anchorage and also conical type of so technically we say that this is the distribution of it. Okay, you can see this is the en bloc. So this is where we want to design as the I would say the transmission line, and this is the distance from the member throughout the tendon. Okay. All right. So anchorage. Okay, anchorage zone. Say that the main reinforcement in the anchorage zone should be designed to withstand the bursting tension. Okay, because that is the purpose of it, which is determined by the transverse stress distribution on the critical axis. Okay, so this is for plate embedded. All right. Typical type of anchorage, the typical Richmond reinforcement can be seen in figure 5. So this is where you can see typical type of post tension tendon and also anchorage. So this will be the tendon, and this will be the anchorage. So this is the chronicle part. the chronicle whereby is embedded inside the specimen. Okay. All right. What else? We have met helix loops or links are generally provided in particular directions. So you can see this is the whole view. So how is it being linked like this is an option, all right, for us to counter for any downstream condition. So based on the research work, helical reinforcement is more efficient than mat reinforcement. So they do consider that the helical one yang macam spiral tu is much better, okay, performance. All right, boleh everyone so far? Can you follow? Ada ke tidak orang tu? Atikah ada ke? Danish? Alia? Sarah ada. Okay, all right. So like I mentioned before, this topic is not that difficult, to be honest, and we gonna cover the calculation as a general condition, all right, as a for you to understand the topic better, and what we call that. But then it's not what you call this topic is whereby we cover it lah. I mean for for you to understand it more better. Yeah. All right. So example. So we have one example. What are we covering? For this topic, we're only we're gonna do one example. Okay, the second example
Apa dia? Main ML kat kata. I tak suka buka mic. Main kat bilik I lah. Tapi main ML lah. Nak buy one. Sekali buy one. Kalau satu baju benda. Sila lah.
Okay, all right. Let's take a look on the example. So we have two examples actually in this note. But then I will not cover both. I only gonna cover one example. So for the second example too, we're just gonna go through quickly. All right. So we'll not go in detail one by one. Okay. All right. Let's take a look on the example for this, shall we? All right. So this example is covering for pretension. Okay, pretension beam. All right. So technically, what we see here is what given is the I section. Okay, I section beam. And the span, the length of your beam given as 8 meter. So the dimension is shown in figure. So the dimension and the member is pre-stressed by 8 wires. So it has 1, 2, 3, 4, 5, 6, 7, and 8. Okay, of 5 mm diameter located on the tension side, means dekat bawah neutral axis. Alright, at effective eccentricity of 9 mm, 90 mm. So dia tak ada measure one by one of the layers lah. So they take averagely as a 90 mm. Alright, what else? The initial stress is 1280. So that will be the initial. Right, and the tube strength of the concrete is 42 MPa. Okay, so determine the maximum vertical tensile stress developed in the time transfer zone. So we have to calculate what will be the vertical tensile stress, and for us to design suitable mild steel reinforcement, assuming the permissible stress in steel is 140 MPa. Okay, all right. So kalau you look into this, what is given to us, yeah. So means that you have certain values. So we have the forces that involve, all right, of the stresses, from the top flange until the bottom part of your beam. Okay, so later we will see the calculation. All right, so now when we have the stress distribution, so because the first question is you need to determine what will be the vertical tensile stress. So when you calculate the total pre-stressing force, so means that what given to you is the stress. So this is given to you is the stress. So from the stress, okay, when you multiply with the area, okay, which is the diameter is given, which is 5. So you can calculate the total area, which is the number is 8. So multiply the area, okay, multiply with 8, then multiply with the stress, you will get the force. So this is will be the initial pre-stressing force, because what given to you is the initial stress. Okay, so now with this value, right, you can calculate the total stress at bottom fiber and also top fiber due to the pre-stressing only. All right, so with this calculation, because you know your P berapa and you know your E position of your tendon, you know the area and also your Z, okay, because of the information given to you. So the stress at the top, when you put it all the parameter inside the equation, you can calculate the top fiber and top stresses and also bottom stresses. So technically, if you transfer it to the diagram, so you will get 8.6, okay, and 0.06. So 0.06 will be a bit almost equal to 0 lah, right? And you have 8.6 because you have the top fiber and also the bottom fiber, okay, of your stresses. So then that will give you 0.06, all right, and also 8.6 for bottom stresses, yeah, at the bottom fiber. Okay, so we have this one bottom, and then we have top, right? 0.02 is almost 0 lah. Okay, so then we want to calculate what will be the total moment area. So moment area, whereby we get from these values of the triangle stresses, okay, and you'll be able to get the, how to say, the height of each of the position, okay, of your stress block, of your stress distribution. So you can interpolate it to get the values for each of the stresses along your stress diagram. So you have, for example, you get this 2.8, okay, means that you have stress multiply with the area multiply with lever arm. So lever arm will be taken into consideration 170 as this. Okay, so this is 170. Yeah. So we have 200 times 60 will be the area. Okay, so 0.64. So 0.64 will be at this particular area. So these forces or this stress, they are happen at the center part of your, for example, 0.64 happen, okay, at the center part of your flange. Okay, 2.8 happen at the center part of your web. Okay, so the distance for each will have for 0.64 is 170, and this one will have 70. So with this, you can interpolate like, because you know the maximum triangle of your stress is 8.6. So then you can interpolate to get 0.64 and also 2.8. So with these values, okay, you'll be able to calculate your lever arm. Okay, because stress multiply with your area, you get the force. So technically, this is your force. Okay, so this particular part is actually your force. So multiply your lever arm, which is your Z, and you will get will be your how to say, your moment lah. Okay, your M. So the same goes with the second part, which is 140. This is the 140. So multiply with your AT and M, okay, which is the height of your web. This is particular part, and you multiply with 2.8, which is you get from the interpolation of your stress triangle, and multiply with 70, which is the height of your force. So technically, you get the total moment will be equivalent to 351 multiplied by 4 Newton per meter. Okay, so based on that values, okay, you can also calculate your transmission line according to the formulation as we highlight above before. So technically, you must times 0.5, consider the tandem factor and so on, 1,280 divided by 4.03. So at the point of this equation, you get 397. Okay, all right, so all this parameters is already decided for you. Okay, and you calculate your MPPT for the bond stress and everything. So you put into the equation, you got the total. All right. So another method for us to calculate our transmission line is by using table 8.1. So table 8.1 will give you the value of your beta B. Okay, so beta B can be taken by considering your concrete strength and also the type of your strand. Either it's a strand normal wire ataupun lead wire. Okay, so with this you can, for example, you choose it to be a strand with smooth and indented, so means that you get 65 in there. So 65 multiplied with the diameter, you get 325 mm for the length according to the table. All right, so taking the steel stress is 140, which is limited to 300 Newton. So no need to check on fact. So the required reinforcement, because we want to know how much is the area, okay, of your reinforcement that we want to provide for our link. So we have area required is 2.5 multiplied with the moment, which is you calculated the moment that required by your M block, which is you have this 351. Okay, so then divide by your 140, which is the strength of your steel, and multiply with your height. So technically the area you get 157 mm squared. Okay, so with this we can provide 3 bars 6 mm closely, right? So means that say at 50 mm, 200 and so 350. So along the line too, there are certain position where you're going to provide 3 bars and 6 mm closely. Okay, boleh everyone? It's a quite straightforward calculation, nothing fancy about it, ataupun nothing that is how to say difficult to understand. So I think so far sepatutnya is clear lah. Okay, so we have next design of M block reinforcement. Okay, so the beam below is stressed by 4 identical 100 mm diameter conical anchorage. So bila conical, normally you would see that it's a bulat lah. Conical ni normally tak akan bulat. So macam dalam gambar atas tadi. So flat normally will be square, but conical will be a circle lah. All right, and anchorage located as shown. So we jacking force 250 kilonewton applied to each. So the area may be subdivided into 4 equal end zone, which is we have 200 times 100. So you have the equal zone tu, maknanya dia dah divide by area of a square. So you have 200 multiply 150 mm each. Okay, maknanya dia pecah, dia divide according to the anchorage. So determine the reinforcement required around the anchorage. So how much you want to provide? So at this point, you ada values of concrete strength, you ada FIK steel 500 and consider one anchor. Maknanya kita akan design for one anchor sahaja. Kita tak design for every anchor sebab it's applicable kan, sama. So first you check bearing stress under the anchor. How to check the stress? Okay, so means that you can calculate the stress lah. So the stress is quite straightforward, whereby you are the pre-stressing force divided by area multiplied with gamma P, which is the tendon. So P we take as a 1.2 at this for this N block. So then the total bearing stress is 38.2 MPa. All right. So now we want to check out. We want to calculate our allowable. So actual is what is applied lah, kan? What is applied. So allowable is normally by code. So by code, normally you have a certain specific formulation that we have to follow. For example, according to the code, we have 67% right of your stress. Maknanya you punya stress multiply with what it calls 0.67 multiply with your concrete strength. And AC1 divided by AC2 is more on the ratio wise. So means that kalau kat sini, you tengok AC1 is the area of the whole part. Maknanya not AC0 will be the area of where you have your conical, so which is equivalent to 100. This one 100 mm conical. Okay. So the diameter of conical is 100 mm. So AC naught is the diameter of the anchorage itself, okay, of conical anchorage, and 150 is actually the area of this particular part. Yeah, saya just nak tunjuk balik. Is this particular part, yeah? This 150. So since that, walaupun the area tu you nampak square, but since that we are taking ratio of 2 AC naught, so then we take 150 as the full diameter and multiply with 3, multiply power of 2 divided by 4. So allowable bearing yang we can calculate from this is 40. Okay, so 40.2. Okay, so actual yang apply is 38. So for the design of the conical yang kita dah provide tu, we can provide 40.2 strike. So means that is safe lah, is okay lah. Okay, still okay. Alright, now we look into the reinforcement. Okay, so when talking about reinforcement, we talk about from figure B, which is this particular part. So we have the tensile force in the tie of equivalent of stresses, yeah. So this is nampaklah kita punya trusses ni. Okay, so bila kita ada resultant trusses like that, we're always gonna go for resultant. Okay, so 0.33 is taken by these values. Okay, 0.33. Okay, tengah-tengah tu. Multiply with 1.2, multiply with 250. So you get what will be your tensile force. So technically, we calculate the area of how much is required. So since that the tensile force is 100 that we calculated, so then multiply with 10 power 2 for Newton and divide with the force, okay, with the stress, 300. Okay, sorry, with the P, precise force. So then you can calculate the area that you need to provide to cater for 100 kN tensile force. So this can be provided by 3 10 mm closed link. So you design whichever that suitable, as long as your design must be more than your applied. Okay, so then for every position of your along the length of the beam, also you will do the same thing. Okay, you calculate. Alright, C, check compressive. Tadi tension, now compressive in the strut. So bila you kata compressive, so you have this formulation to be used. Okay, and the total of it you get 13.44 MPa. So actual stress in the strut itself, so okay, so force is 0.6 multiplied 1.2 multiplied 250. So the cross-set area is this lah, because we are considering 250 and cos 33.7. So cos 33 will be, this is 33 degrees 0.7. Okay, but then we will take into the consideration of the beta value. So this is will give you 7.21 MPa. All right. So with these values, so the effect of combined anchorage can be considered, and by considering the total force is 1000 kN acting on effective en bloc 400 times 400. So that is the conclusion that they give. Okay, and the T is equivalent to 400. Okay, and the area is equivalent to 1500. So kalau you tengok the detailing for the en bloc part, so this is where you have 3T10, and also this is where you have 5T16. So really depends on by length, which is the maximum transmission length will be 700. Okay, boleh everyone? A bit fast. I'm sorry. Kalau tak faham, please ask. You can always ask for you to improve your understanding on this topic lah. Okay, so yeah, I think technically that's all yang I need to cover. Okay, I still owe you. So alhamdulillah, I managed to pay my debt. Okay, ada hutang. Alright, alhamdulillah. So saya pun risau bila lah saya boleh ganti. Alright, and Allah izinkan tonight for me to replace it. And just for your information, I know you might not need the platform to ask question, but I just provide the platform. Okay, during the study week malam, Okay, for us to, because technically I don't, for your class, I don't have any replacement class because your class is taken by Dr. O. But since that for other group, they have what we call, they have they need, I need to replace because other 1 week to I'm not around, I was not around. So then therefore I take the opportunity to use the 2 hours of the replacement to open up online platform if any student have problems during their preparation for your final exam. Okay, so do feel free to join, okay, any of the platform, all right, or any class that you think you want to join ataupun to ask question. If you feel that suddenly malam Isnin baru you start study ke ataupun the Tuesday baru you have question to ask, then just join the platform. Okay, inshallah I'll be around to help out. Okay, and it really depends on if you have question or not lah. And you just call me my name, then I will assist you in online. All right, so yeah, I think that's all for your group. I'm so sorry for my my delay in terms of covering this topic. Okay, and alhamdulillah we still managed to cover it lah before our end semester. So towards the end, I just want to say thank you so much for the the first 7 weeks you guys with me. All right, and if say that there's anything wrong or apa-apa, so saya minta maaf lah. All right, so if you need any consult on anything, so please you know where to find me. You can just come to my room at any time, inshallah. I can help you out in anything that you feel need helps. Okay. All right. So I think that's all. Thank you so much, guys. Do take care, and I do wish you all the best. Okay, especially in your final exam for our pre-stress course. All right. Thank you so much, guys. Assalamualaikum. Don't forget your attendance.
Thank you, doctor.
Thank you.